In this video, we complete the derivations of the derivatives of arcsine, arctangent, and arcsecant using implicit differentiation. Because we know the derivative of sine, tangent, and secant, we just don't know the derivatives of their inverse functions. Let's say we start with y equals arcsine of x, and we want to write that equation in terms of functions we know the derivative of. So then we take the sine of both sides. The sine of the arcsine of x is just x. And now I have sine of y equals x. I'm trying to figure out what the derivative is, so I will differentiate both sides with respect to x. The derivative of sine of a function of x is cosine of that function of x times the derivative of the inside. In this case, our derivative is dy dx. And the derivative of x on the right-hand side is 1. Then I want to isolate dy dx. I just divide both sides by cosine of y. And we get dy dx equals 1 divided by cosine of y. But we'd like to write our answer in terms of functions of x rather than this function of y. And so we'll draw a triangle. We know that sine of y is equal to x. So if this is my angle, and x can be written as x divided by 1, we can use this to label the sides of our triangle. Sine is opposite over hypotenuse. So when the side opposite of y is x, our hypotenuse is 1. And since we know two sides of the triangle, we can use the Pythagorean theorem to find the third side. If I call this side a, I know that a squared plus x squared equals 1 squared, which is just 1. If I want to get a by itself, I subtract x squared from both sides, and then I take the square root. And because this is a length, I'm going to use the positive square root. So a is actually the square root, positive square root of 1 minus x squared. Since I know the sine, and now I know all three side lengths in terms of x, I know the ratio of the side lengths, I can use this triangle to find the cosine. Cosine is adjacent over hypotenuse. This side is the adjacent side. It's next to y, but it's not the hypotenuse. The side opposite the y in the triangle it's the one across from y. That's this one. We call that the opposite side. And then the hypotenuse is the one opposite the 90. So we have the adjacent side divided by the hypotenuse, which is just this function over 1. So our cosine of y in terms of x turns out to be the square root of 1 minus x squared. We substitute that in over here. We get dy dx equals that function. And remember, the function y was just arcsine of x. So that ends the proof. The derivative of the arcsine of x is 1 divided by the square root of 1 minus x squared. And that's it. Gives me the slope at various values. When x is plus or minus 1, we've got a 0 in the denominator. So the slope is very large and positive as we get close to x equals plus or minus 1. And when x equals 0, we just get a 1 for the slope. So this is what my graph looks like. Like we've taken the sine graph and we've drawn it on its side. But then we've restricted ourselves to the interval where the resulting graph would be a function. So our x values go from -1 to 1, and our y values go from -pi over 2 to pi over 2. So we took a restriction of the sine graph from negative pi over 2 to pi over 2 to get this in the first place. And so that's our arcsine graph. And then this function is going to have some asymptotes. Again, when x is 0, we're going to get about 1, or we're going to get exactly 1. This number is about 1.5 because pi is approximately 3. So 1 is about 2/3 of the way to that pi over 2, so it's right there. And then x equals 1 and x equals -1 are our asymptotes. So I think the derivative should look like that. And we can graph it on Desmos.com and see if the graph on Desmos agrees with this. But I hope that graph agrees with your intuition as well. When you look at this arcsine graph, if you draw the tangent lines, they all have positive slope. This is a very, very steep positive slope, and the line over here would be a very steep positive slope, but this one in the middle, if I drew a line, it would just have like sort of an ordinary slope of say 1 or so at that location. So hopefully that makes sense. The slope is always greater than 1. And as we get closer and closer to those boundaries, the derivative values get very large. The slopes get very, very steep. Okay. I'm not going to graph that on Desmos right now. I'm gonna keep going. Let's do the next derivation, the derivation of the arctangent derivative using implicit differentiation as well. We know that y equals the arctangent of x. And we're trying to find the derivative of that. So we want to write this in terms of functions that we know. So to get rid of the arctan, we'll take the tangent of both sides. The tangent of the arctangent is just whatever you started with. So in this case, it's just x. And now I've got an equation where I know the derivative of the function on this side. I know the derivative of the function on this side. The only unknown here is y. So we can use implicit differentiation to find the derivative of y. So we take the derivative of both sides with respect to x, remembering that y is this function of x with an unknown derivative. And the derivative of the tangent of any function is secant squared of that function. Since this is a function of x, we'll put that function of x back inside and multiply by the derivative of the inside by the chain rule. And then the derivative of x is 1. And so we're trying to get dy dx by itself. It's multiplied by this extra factor. So we just divide. We have 1 divided by secant squared y is our dy dx. Now we don't want our answer in terms of y, we want our answer in terms of x. So we're going to draw a triangle again, just like we did in the last problem. We know that tangent of y equals x. So if this angle is y, and that the ratio is x divided by 1, remember in terms of opposite, adjacent, and hypotenuse, this is opposite, this is adjacent, and this is the hypotenuse. And all the similar triangles, regardless of this angle here, these ratios are all going to be the same. Not regardless of the angle. When we know the angle, the ratio of these sides is all going to be the same. So even if the triangle is larger, if the triangle is smaller, it really doesn't matter what the size is. The ratios for that define the tangent, the sine, the cosine, and all of that, those are going to be the same either way. So here we're saying tangent of y is this ratio. It's x divided by 1. And in this case, it's tangent is the opposite over adjacent. That's how it's defined in terms of these right triangles. So we're saying that when the opposite side has length x, the adjacent side has length 1 for that particular angle. And so if this is x and this is 1, we can use the Pythagorean theorem to find the length of the third side. This side squared plus this side squared equals this side squared. So we're going to have 1 plus x squared. And then we take the square root to get the hypotenuse. So that's the tangent of y. And this is actually, the dy dx turns out to be 1 over secant squared or cosine squared y. So we just need to find the cosine of y and then square it in terms of x, and that's going to give us our derivative. Well, cosine is adjacent over hypotenuse. So what our adjacent side is 1 when the hypotenuse is square root of 1 minus x squared. I must have done that wrong. 1 plus x squared, excuse me. And we square that. We square the square root, we just get whatever was inside. So dy dx turns out to be 1 over 1 plus x squared. And y was arctangent of x. So now we know that the derivative of arctangent is 1 over 1 plus x squared. Now we can graph that. Graph that by hand. The arctangent graph looks like this. It comes from taking one of the branches of the tangent graph, the one that passes through the origin, sort of turning it on its side and switching the roles of, when we switch the roles of x and y. It's like you turn it on its side and then you reflect it. And then this gives you, and this is what the graph looks like. Since the tangent graph has asymptotes at y equals negative, or x equals negative pi over 2, and y, or x equals negative pi over 2, and x equals positive pi over 2, and you switch the roles of x and y, you have horizontal asymptotes, negative pi over 2 and pi over 2. And we just have one branch like this. If you draw a bunch of tangent lines there, I hope you can see that all of those tangent lines would have positive slope. If I draw a tangent line, as I look at it from left to right, it's increasing. Well, that's consistent with the graph of the derivative of arctan. The derivative is equal to 1 when x equals 0. And since pi over 2 is about 1.5, that's about 2/3 of the way to pi over 2. And then as x gets larger, this denominator gets larger. But it's always positive because x squared is always positive, and then you add 1, so it's positive. So it stays positive. So as x gets farther from 0, this denominator gets larger and larger. So the fraction gets smaller. And it looks like that. And because of the x squared, if I replace x with negative x, when I square it, the negative times the negative makes a positive anyway. We're going to have symmetry. So you're going to see the same thing on the left-hand side that you see on the right-hand side. And so this turns out to be the derivative of this. I think that that's consistent with our expectation. If we draw a tangent line, if I draw a tangent line here, it's reasonable that I would say that the slope of the tangent line is 1. And that that all of my tangent lines have positive slope, but they get closer and closer to 0 the closer we get to our asymptotes. I think we can all see that. As I get farther away from x equals 0, like x equals 100, the slope is going to be 1 divided by 1 plus 100 squared. So it's just 1 over that larger number. This is a very small slope when x equals 100. So this is very, very flat. Very close to flat, but it's not completely flat. It's continuing to increase. This is always positive. It's just not a very large number as x gets large. But when x is near 0, it's a 1. All right, so that's our arctangent derivative, and arcsecant is very similar. We're going to do the last one. So we don't know the derivative of arcsecant, but we know the derivative of secant. So we can use that to find the derivative of secant, or excuse me, arcsecant. Start by taking the secant of both sides. And the secant of the arcsecant is just whatever you started with. Since those two functions are inverse functions, they undo each other. We've got secant of y equals x. And then we differentiate both sides with respect to x. Now, the derivative of secant of y, where y is a function of x, is secant of that function of x times the tangent of that function of x times the derivative of the inside. And then that's equal to the derivative of x, which is just 1. Bless you. So we can get dy dx by itself by dividing by this. And then we're very close to stating that answer in terms of x. I don't want it in terms of y, I want it in terms of x, so I draw my triangle. Y is the angle here. And we're going to label these sides in terms of x. We know the secant is x divided by 1. The secant of y is x divided by 1. And secant is 1 over cosine. So I'm just going to write cosine is this, the reciprocal of this, it's 1 divided by x. Cosine is adjacent over hypotenuse. You may have heard of SOHCAHTOA. I've always wanted that t-shirt. I'd never purchased it. The one that says Camp SOHCAHTOA on it. It has like the mountain in the distance. This helps you remember. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So I really think in terms of sine, cosine, and tangent, and then take reciprocals to think about secant, cosecant, and cotangent. So when they tell me this is my secant, I say, okay, let's write it in terms of cosine. Reciprocal of secant is cosine. So I say cosine of y is 1 over x, which is adjacent over hypotenuse. So the side that's adjacent to y is the side that's next to y, but it's not the hypotenuse. It's the other one. That's this side. That turns out to be 1. And then the hypotenuse is x for that particular angle. And we say, okay, we know the hypotenuse, we know the adjacent side. What is the third side? Well, according to the Pythagorean theorem, 1 squared plus b squared has to equal the hypotenuse squared, x squared. So we can get b by itself by subtracting 1 from both sides and then taking the square root. And so we get b equals the square root of x squared minus 1. Now we need our answer in terms of, or we need secant and tangent to substitute right here. Actually, I'm still thinking in terms of sine and cosine. So this is secant is 1 over cosine. Tangent is sine divided by cosine. And so if I multiply those two together, I've got 1 divided by sine of y divided by cosine squared y. And then I've got 1 divided by a fraction, so I can flip it. All right, so that's what we have. And now I know what cosine of y is in terms of x. It's 1 over x. And then sine of y is opposite over hypotenuse, which is this square root. That's our opposite side. The side opposite y in the triangle over the hypotenuse, which is x. Oops, the opposite side is that square root of x squared minus 1. So we end up with cosine squared, which is 1 over x quantity squared, all divided by sine of y, which is the square root of x squared minus 1 divided by x. So you've got two fractions, you're dividing them. You keep the fraction in the numerator the same, and you take the one in the denominator and you flip it and you multiply. One of the x's will reduce. And so you get this. Now there are some restrictions and I really need to look those up. I don't remember the details. But the derivative is always positive. So we always have to have an absolute value of x here rather than just an x. So there's a little bit of hand waving at the end of my derivation here because this is not, there's some details missing. But I've just shown that the derivative of y with respect to x should be 1 over x times the square root of x squared minus 1, provided that x is positive. And we're thinking of x as positive. And it turns out that we always want it to be positive. So what have we shown? The derivative of y, where y is the arcsecant of x, is this 1 divided by x times the square root of x squared minus 1. But the formula is actually like this. We need the absolute values. And I believe it's related to domain and range just used for the arcsecant graph. I don't remember what those are. All right, so that's our derivation. If we want, we can look at the graph of arcsecant. In order to do that, it's helpful to look at the graph of both cosine and then secant. So cosine looks like this. Cosine is 0 at all of the odd multiples of pi over 2. And secant is 1 divided by cosine. So every time that cosine is 0, our secant has asymptotes. At x equals 0, well, this is the cosine graph, sorry. Secant is 1 over cosine of x. So when cosine is 0, secant is 0, it's 1 divided by cosine of 0, which is 1. 1 divided by 1 is 1. And then when we're dividing by a tiny positive number, we get a large positive number. And so that happens here and here. And then when cosine is, or when we plug in pi, we get, that's -1 for our cosine graph. Then this is 1 divided by -1, our secant is, so then we get -1 there. And then here, as we approach the asymptotes, we're dividing by a tiny negative number because the y values on the cosine graph are negative. So our graph goes to -infinity as we approach those asymptotes. And that repeats over and over again. So that's the arcsecant, but when we take the inverse of the secant, we restrict ourselves to a particular interval. We want the resulting function to be 1 to 1. The problem is right now, this function doesn't have an inverse because if I draw a horizontal line, it crosses infinitely many times. So we need to restrict ourselves to the interval from 0 to pi. So, or to an interval that includes the entire range. And we choose to restrict ourselves to the interval from 0 to pi. It's sort of mathematical convention that we all choose to restrict ourselves to that interval. So we're just taking those two parts of our secant graph, and then we're going to switch the roles of x and y. Notice that the range of secant is -infinity to -1. So we go from there all the way up to -1. Then we skip all the values between -1 and 1, and then we go from 1 to infinity. So that's the range of the secant. And the domain is typically all real numbers except those that cause the cosine to be 0. But we're taking a restricted, or we're using a restricted domain of 0 to pi. But we exclude this one x value. So from 0 to pi over 2, and then pi over 2 to pi. And we just take that restriction so that we can define the arcsecant function. And so it's actually a function. So what used to be the range of the secant is now the domain of this function. So our new function is defined on the interval from -infinity to -1, and then the interval from 1 to infinity. So it skips all the x values between -1 and 1. And then this vertical asymptote at x equals pi over 2 becomes a horizontal asymptote at y equals pi over 2. when we switch the roles of x and y. And this point, when x equals 0, y equals 1, becomes this point. And then this branch approaches that asymptote y equals pi over 2. Or excuse me, x equals pi over 2. So our branch here will also approach the asymptote. And then here we have when x equals -1, y equals pi. So we're right here. And then as we approach the asymptote at pi over 2, that branch approaches it as well. So it looks like this. And then the claim is that this function is the derivative of this function. Now, a few things. If you look at the graph of x squared minus 1, that's just a parabola shifted down 1 unit. So we can't actually take the square root of x squared minus 1 unless we're on the interval from -infinity to -1 or on the interval from 1 to infinity, which is fine because that's not part of the domain of the inverse secant or arcsecant function anyway. But as we get close to plus or minus 1, we're going to have something that's very close to 0 here. So our function is going to have asymptotes at plus or minus 1, the derivative function will. And let's look at the slopes. This is always positive. Absolute value of x is always positive. And as x gets very large, the absolute value of x also gets very large. So we're going to have 1 over something very large, which is very small. So I would expect my derivative graph to look like this. And there's some symmetry there as well. All of the tangent lines, if we draw our tangent lines, they all have positive slope. And as we get closer to that point there, the slopes get steeper and steeper. But as we go to -infinity or positive infinity, the tangent lines sort of get flatter, less steep. The slopes approach 0. Again, got very steep lines in the vicinity of this point, but then the farther out we go from x equals 1 or x equals -1, or either to the left or to the right, the slope approaches 0. So that's our graph. We've got y equals, or y prime equals 1 divided by the absolute value of x times the square root. That's it. And we could graph this on the computer. The computer is going to show you the same thing. But we can infer what these graphs look like as well, just by looking at the equation of the function. Thinking about when the denominator is 0, and then thinking about what happens as x gets very large in either direction. Okay, so we did the derivations of these 3, arcsine, arctangent, and arcsecant. The derivations of the other 3, cosine, cotangent, and arccosecant, are going to be very similar. The only difference is when you take the derivative of a cosine function or a cosecant function or a cotangent function, when you compute that derivative, you're going to have that -1 as a factor out front. So you end up with a -1 in the corresponding derivatives for all of those. So I'm just going to state those, and you can do the derivations yourself and make sure that you get the right answer. You can think about that absolute value as well and think about where that comes from and why that's important, why that's true. But I'll just state the other derivatives for you. The derivative of arcsine, we just derived to be 1 over the square root of 1 minus x squared. If you do the derivation, you'll find that the derivative of arccosine is almost identical, but it has a -1 in the numerator. And then we found that the derivative of arctangent of x is 1 over 1 plus x squared. If you do the derivation, you'll find that the derivative of arccotangent is the same, except we've got a negative in the numerator. Kind of messed up there. And then for arcsecant, there was a little bit of hand waving at the end with that absolute value. But We almost derived this except for the absolute value part. They've said that the derivative is 1 over the absolute value times the square root of x squared minus 1. And if you do the derivation, we'll find that the arc cosecant has a -1 in the numerator, but is otherwise the same. All right, that's it for the derivations. And I believe that's the last video for implicit differentiation as well, excuse me. Let me know if you have any questions.